Okay, in this video I'm going to demonstrate how to carry out a confirmatory factor analysis in LISREL after importing data from SPSS into the LISREL program. So the first step in this process is just importing the data into the LISREL preprocessor known as PreList. So we're going to click on File, New, File and Import Data, and when you click on those, this box will open up here, and over here you've got various file types. So you've got free format data by default, but when you click on the arrow you've got comma delimited, tab delimited, SPSS, and other formats. So we're going to go with SPSS because that's what we're importing from. So you can see I have a couple of files right here, and I'm just going to use this file right here, SPSS SAV file, and then click on Open. And so when I click on that, now it's asking me to give a name to a LISREL system file. So basically what's going to happen is that the SPSS data file is going to be converted to a LISREL system file, and that file then can be manipulated in various ways in PreList, and ultimately we can utilize the data from that file in LISREL. So it went ahead and gave me a default name that was consistent with the SPSS file. So I could give this a different name if I want to, but I'm just going to stick with this. And at this point I'll click on Save, and now you'll see that our data file is open. So I've got data on 7 variables, 7 continuous variables. And the sample size is, I believe it's 200. So yeah, we have 200. So at this point, the next step is actually kind of defining what our variables are and dealing with addressing the issue of missing values and so forth. In this particular data set, actually I don't have any missing values, so we won't do anything with that just yet. But we'll go to Data, Define Variables, and then I'm just going to actually highlight everything because all the variables are going to be treated as the same type. So if I click on Variable Type, you'll notice that you've got ordinal variables, continuous, you have censored, and so forth. The data are being treated as continuous, so I'm going to click on Continuous and then on OK. Under Missing Values, if there were any missing values in the data set, then I would, under missing values, I would give the code for that. A lot of times when you import data from SPSS, if you have just blank cells with no missing value codes, then what will happen is in LISREL, or in PreList, or in this particular file right here, we would basically have a cell that had -999,999, but we don't have that in this case because we have a complete data set. So at any rate, we're going to say we have no missing values for this particular data set, and then we'll click on OK. So at this point, to do anything else, we need to save this file. So basically, we need to tell the program that we want any subsequent analyses dealing with these variables right here to be treated. We want the variables to be treated as continuous. Now, under statistics, you have various options. You have data screening. You have various output options that you can ask for. For right now, we're just going to look at data screening, and if we click on that, you can now start to look at your data and get an idea about it, some of its characteristics. So a lot of the data screening can be done in SPSS or whatever statistical package that you're working with, but this is kind of one of the nice things in PreList. So you can see you've got your variables, you've got the means for those variables, standard deviations, skewness and kurtosis values, and then you also have even tests of univariate normality for those variables. So as you can see right here, really none of the p-values for concerning the tests for skewness or kurtosis or for both skew and kurtosis. None of them were actually statistically significant, which would suggest that we actually have reasonably normal distributions for those variables. So at this point, we can go and go under File, New, and now we're going to click on Simplest Project and then on OK. And so now we have to give our simplest project a name. So in my previous video, with basically it was the same data set. It was just I gave you a matrix summary for the correlation matrix and standard deviations. We basically just typed in the syntax for our confirmatory factor analysis. In this video, we can use some of the menu options to set things up. So I'm just going to call this CFA and just basically leave it as that. And so the file extension will be .spj, and that's for a simplest file. So as you can see, this file is now opened up, and you can see at this point that now we can start to put in our syntax, but we can use this little setup wizard here to do this. It makes life really a lot easier. So under setup, we can go to title and comments. I might just title this confirmatory factor analysis, and then click on next. We don't have multiple groups, so I'm just going to continue on. And now under this particular box, I'm going to click on Add Read Variables. So I'm going to click on here, and you'll see you've got a little drop box right here, and I'm going to click on LISREL System File. So I'm going to click on that, and then under Browse, I'm going to go to the LSF file that was basically saved previously. So I'm going to click on that and open, and then click on OK. So now it's reading those variables from our earlier LISREL system file data that we had into LISREL. Now I'm going to add latent variables. So in this case, I'm going to click on this, and the first latent variable, I'm going to call it esteem, and then I'll click on OK. And then the next latent variable, I'm going to call it efficacy. Okay, because the measured variables in our data set are capturing responses to 7 items on a survey. So 3 of them were designed to measure self-esteem, 4 of them were designed to measure self-efficacy. So at any rate, next I'll click on next, and really there's nothing else to do at this point, so I'm going to click on OK. And if we go back to setup, now I can click on build simplest syntax. So I'll click on that, and so now it creates a basic syntax file for me. So this is my title line that you see right here. This line right here is telling LISREL to pull the data from this LISREL system file. So it's reading the data from that file. We could have typed in the syntax for doing that without the wizard, but it's a heck of a lot easier just to use the wizard. So then under latent variables, you can see we have esteem and efficacy. We have a line for relationships, then we have path diagram, and end of problem. So what I'm going to do at this point is for the relationships, I'm going to specify, you can see too, by the way, that when we clicked on build the syntax, all these the observed variables become evident down here in the observed list, and we have our latent variables right here. So at this point, what I can do is I could say, basically I have SE1, SE2, SE3 are used to as indicators of the latent construct self-esteem, and F1 or EFF1, EFF2, and so forth are used as observed indicators for the self-efficacy construct. So we could either type in the variable names directly, or we could actually drag and drop. So the thing is that following the relationships command, we think about our observed variables. the variation as being produced by our latent variables. So we're adopting sort of a common factor analytic approach, and so given that, we will have the observed indicator variables on the left side of an equals, and then on the right side of the equals will be the latent variables. So we're basically specifying the equations for the model. So for the first thing, we'll move self-efficacy. I can actually drag this up here, and I can highlight SE2 and drag it up, and then SE3 and drag it up, and then equals, and then I'll just type in esteem. And then from there, I can drag up EFF1, EFF2, 3, and 4. And then type in efficacy. So this is my basic factor analytic model. So basically self-esteem is assumed to be accounting for the variation and as well as a covariation among these measured variables here, which were items on the scale designed to measure self-esteem. And then we have efficacy basically predicting these measured variable responses here. So at this point, I'm going to highlight everything and click on Run. And so now we have our analysis, our basic output. So you can see that we've got you've got basically, if we go to estimates, these are basically unstandardized factor loadings. So basically you can say that esteem is essentially kind of accounting for or predicting the variation in these measured variables, efficacy accounting for or predicting variation in these variables. So that's what the unstandardized factor loadings are. Over here, the arrows pointing to each of the indicator variables. These numbers, these values right here, are referred to as uniquenesses. Basically, it's variation that is specific to the measured variable or observed indicator that is not being accounted for by the latent variable. So this could be, measurement error of some sort, or it could be method effects. Just anything that's extraneous to the model that is not actually built into the model is being accounted for on this side of the indicator variables. So at this point, and this double-headed arrow right here is between the esteem and efficacy factors, is basically the correlation between those factors. If I want to determine if which of these parameter estimates are statistically significant, I can do the little drop down and go to t-values, and you can see that these are all the t-values in the model, and basically, for a non-significant parameter estimate would actually appear in red, and essentially we're using a threshold of 1.96, either positive 1.96 or having a t-value greater than 1.96 or less than 1.96 to be statistically significant. So you can see that none of our parameter estimates in the model actually are non-significant. So that's actually kind of suggestive, in that respect of fit to the data. But there's more in assessing fit than just looking at the individual parameter estimates. There's also just the question of overall model fit, and that's where we utilize various fit statistics. The chi-square goodness of fit test that you see right here is basically, to use Klein's terminology, a badness of fit index. And basically what we're looking for is a non-significant p-value. So non-significant p-value would actually suggest that we have a reasonably good fitting model. Basically what's happening when we're assessing fit using this test is we're comparing the sample variance covariance matrix against a model implied covariance matrix, and the degree of to the extent that there is misspecification, there will be less fit between those two matrices. So if we find statistical significance, then that would actually be suggestive that we have a lack of fit. Now, the downside of the chi-square test is that it's impacted by sample size. It's a significance test, and the end result is that when we have really large sample sizes, which SEM generally is a large sample approach. So when you have large sample sizes, the effect is oftentimes to achieve statistical significance, which would signal that you have a lack of fit of your model to the data. So it's also important then to look at various other types of fit statistics that really provide more of a descriptive approach rather than a significance testing approach in looking at fit. And so what you see right here is the root mean square error of approximation, and basically what you're looking for are values that are about 0.05 or lower. Those values would indicate that you have pretty close fit to the data. A value of 0 would obviously be indicative of good fit. Values less than 0.08 would still be considered reasonable or acceptable, and values that are above 0.10 would be considered indicative of a poor fitting model. So you can see, based on our RMSEA value, that we have evidence of a poor fit of our model to the data. So next, I'm going to move this out of the way and start looking at the output file. And let's see here. Oops. All right, let's try this again here. So I am going to minimize and now go back and just kind of scroll down. You can see you've got your univariate stats again for the variables. Also, there's a test of multivariate normality for the variables, and that's important because we're using maximum likelihood estimation, which is the default estimation approach in LISREL, and so it makes the assumption of multivariate normality. And so you can see right here that looking at skewness, kurtosis, and kurtosis, that that assumption appears to be met. So scrolling down a little bit further, you can see that we have the measurement equation. So you have each of your you have the latent variable on the right side times the factor loading, and equals, and then you've got the measured variable or indicator variable name on the left side of the equal sign. You have the standard error for each factor loading. If you take the factor loading divided by the standard error, it gets you computed z value, and then you have a p value underneath, which is utilized to assess statistical significance. It's kind of strange, to tell you the truth, that the path diagram approach uses t values, and in the output file it's using z values, but for all practical purposes they're going to say the same thing, given that, like I said, SEM tends to be a large sample approach, so it would not, basically the t values and z values will pretty much correspond. So kind of scrolling down, you can see that esteem was a significant predictor of SE1, of SE2, of SE3. Efficacy was a significant predictor of EFF1, EFF2, EFF3, and 4. You can also see the R-square values, and this is basically the proportion of variation in the measured variable or the indicator variable being accounted for by the latent construct. So you could say that esteem accounts for roughly 75% of the variation in SE1. It accounts for roughly 54% of the variation in SE2, 71% of the variation in SE3, and so forth. As we scroll down, we can look at the various goodness of fit statistics. So you have, this is the maximum likelihood chi-square that we saw before. The degrees of freedom for the model is 13. And you can see that, again, that basically this test was statistically significant, which would be suggestive of lack of fit. But it's very important that you look at various descriptive indices as well, given that the chi-square test is impacted by sample size. So we have the root mean square error of approximation. That's what we had seen previously in the path diagram. And then we have various other indices that we can utilize as well. We have the normed fit index and the non-normed fit index. The non-normed fit index is also referred to as the Tucker-Lewis index. And what we're looking for these indices are values that are above 0.90, preferably above 0.95. These are scaled generally between 0 and 1, although for the normed fit index, the values can exceed 1 by a little bit, so you would interpret those values as 1. The comparative fit index is also scaled between 0 and 1, and so you're looking for values around 0.90 or above, and like I said, preferably 0.95 and above. Then we have the standardized root mean residual, and we're looking for values that are less than 0.05. Then we have the goodness of fit index and adjusted goodness of fit index, and we're looking for values for those above 0.90. And so in general, this model is not functioning very well. It's not doing a good job in terms of fitting the data. So we could make model modifications either based on theoretical considerations or hopefully not just adopting a pure empirical strategy like utilizing the modification indices that are presented. But modification indices that are presented in the output can be sort of useful in terms of exploring possible respecifications of the model. But it's really a bad idea just to respecify your model based solely on these indices. Nevertheless, you can sort of look to see, if you add a certain parameter, what the impact is on the chi-square test or the chi-square value. And so, all things being equal, a better fitting model is going to have a lower chi-square value that I discussed just a few minutes ago. So you can kind of look to see where you get the biggest bang for your buck, so to speak. And you can see, like right here we have EFF3 and SE3, suggesting adding an error covariance. So if you add in an error covariance, that would result in a substantial decrease in the chi-square value. You can also see if you add an error covariance between EFF3 and SE1, there would also be a pretty substantial decrease. So you could do that. The main thing to keep in mind, though, is that if you're going to add a parameter based on these indices, it needs to make theoretical sense. It needs to be logical, not just purely empirically driven. Up here, you can see modification indices suggest adding a path from efficacy to SE1 and efficacy to SE3, and these are the decreases that would be expected in the chi-square value. So what I'm going to do at this point is I'm going to respecify the model and just add a couple of those modifications. So in this particular case, I'm going to add up here, I'm going to add SE3 as a variable that is an outcome of efficacy. So in this case, now the model is going to get a little bit more complex, and also I'm going to add in a error covariance. So I'm going to say set error covariance between EFF3 and SE3 free. So in this case right here, we're basically allowing the error variances for these two variables to correlate. So now I'm going to highlight everything and click on Run. And here's our model. And as you can see, by doing this, we have we have our let me just kind of go up here. Here are our estimates, but you can see we've added the error covariance between EFF3 and SE3. We've added in the additional path from efficacy to SE3. So we have basically a much more complex factor structure than what we had previously tested out. So the estimates, these are all unstandardized factor loadings, but we want to keep in mind that basically these loadings right here are representing the idea that esteem and efficacy both account for variation in this particular measured variable. So we'll click on t-values just to see what paths are significant. You see this path actually was not significant. So adding in this path really did not help us out in terms of looking at model fit at this level. You can also see that adding in the covariance right here, it actually turned out that the variance for this variable or the uniqueness for this variable was non-significant as well. But we're just going to leave this in here for the time being. We can also see if we look under standardized solutions, so these are basically standardized factor loadings, and so you can see that the correlation between esteem and efficacy is increased to 0.42. The correlation between the uniquenesses or the error variances is negative 0.21. So if we look at the fit, the chi-square value, you can see that it's still statistically significant. The RMSEA value did drop, but it's still above conventional thresholds for judging a good fitting model. So scrolling down, you can see that we have there's the SE3 variable, and you can see that there's esteem being a significant predictor, so there's our p-value, but efficacy was not a significant predictor. So you can see that basically adding in that path didn't do us any favors in terms of improving fit at that level. So basically everything is interpreted exactly the same way. You can see that the RMSEA value, that this is what was printed out previously. If we look at the norm fit index, it actually improves a bit, and the Tucker-Lewis is a little bit higher, but it's not really indicating too great of a fit. The comparative fit index certainly improves over the 0.90. So there's better fit in that respect. Then we have the standardized root mean residual, and that's above 0.05, which is not indicative of good fit. The goodness of fit index is above 0.90, but the AGFI was still lower. So at any rate, it looks like that we didn't do ourselves many favors by adding in this path from efficacy to SE3. So I'm going to just take this out really quickly and rerun it just to see what the impact is. So I'm going to just kind of maximize our window here, and you can see that with respect to the paths and our parameter estimates, all of them were statistically significant here. Again, this little error variance or uniqueness was not significant, but it's not going to make that much of a practical difference. The standardized solution, we have our factor loadings listed out. You can see the correlation between the two factors was 0.42, and RMSEA actually was a little bit lower, but not substantially so. So I'm going to minimize this window. We'll take one more look at the output file here, and you can see that there's our RMSEA again. You can see the norm fit index was 0.929, non-norm index was 0.901. So both of those are kind of at least meeting the lower bar for good fit, or optimal fit, if you will. Comparative fit index was 0.94, so that's within the ballpark of a good fitting model. The standardized root mean residual is still above 0.05. The goodness of fit was above 0.9, but the adjusted was still low. So basically, we end up with sort of mixed evidence for the fit of the model. The paths were all statistically significant in the model, but in terms of the overall or global fit, we have some mixed evidence for the fit. Just kind of keep in mind that the fit statistics provide they're calculated differently, and they provide different lenses for assessing model fit. So you just have to kind of keep in mind what those fit statistics represent in order to further unpack how you interpret the overall fit of the model. So at any rate, I'm going to end this video now, and hope you find this useful.